Morning, everyone. So today I just wanted to give you a quick overview summary of chapters 4 on naming and chapter 6 on reactions. This is going to be some of the main points that we've covered in each of the chapters, along with some practice questions to hopefully help you with your review. So starting off, we're going to have chapter 4. Although they do call this chapter here nomenclature, nomenclature is just a very fancy word for naming of compounds. You had started seeing naming of compounds back in Science 9, Science 10. We did focus mainly on ionic compounds. We saw a little bit of new stuff with acids and bases and hydrates. There's a few little new steps to it, but a lot of this here should be just reviewed from previous. So we've learned that there's two main types of bonding. Most of our naming rules here focus on ionic compounds. Just for simplicity, we can use the easy way of recognizing it here. If ever I have a compound that's made out of a metal and a non-metal, probably that compound here is going to be ionic. Metals are on the left side of your table, non-metals are on the right-hand side of the stair-step line. Under the ionic family, we had a couple different subcategories. Starting off here, we had just plain old binary compounds, binary meaning just two-part compounds. Just for this part here, we always put the metal first. The non-metal comes afterwards, so in that order, and then the rule was we would change the ending so that it ends in IDE. So pretty much everything that ended in IDE, we could represent, it's probably ionic, it's probably the non-metal that's changed the ending. As we swapped in a few other families here, we threw in, sometimes we had what's called a multivalent metal. This is going to be a metal that has many different oxidation states, many different charges, abilities to bond. Usually, they're close to the transition metal section, okay, so that middle portion of the table. For this one here, we needed a Roman numeral to actually identify which charge is actually currently using. So for this one here, likewise, we're going to put the metal, but we're going to add one extra thing in the middle. So a bracket, we're going to use the Roman numeral to actually identify which charge is it currently using to actually end up forming this compound. The non-metal does come towards the end, so non-metal, and just like previously here, we would change the ending to an IDE ending. Chemists are lazy, so although even for binary compounds here, I could also show you the Roman numeral, I really only want to indicate that Roman numeral for the charge in case the thing has multiple charges. Sometimes, more often than not, it's going to be the non-metal, but we have seen positives that are also polyatomic. But we had seen these groupings here. These polyatomics here essentially are molecules, but somehow, although they're covalently bonded together, they still overall have a charge. In this case here, we're just going to utilize the common names on the chart. So we had common names like sulfate, phosphate. You can always just check it against the chart there. Don't try to name those parts there by yourself. Just look up exactly what the name is. Specifically for those ones, they will probably end in either ATE or ITE. Those ones already had their ending, so you don't change the ending anymore. We looked at acids. Okay, so acids are things that, by definition, they release a proton, they release an H plus every time they're dropped in solution. So not only do they have to have an H, usually we sort of sum that up here, it's going to be H with something, where the A can be HCl, HBr, H2SO4, things like that. Not only does the thing have to hold an H, it has to be able to release this H here when it's in solution. Under this category here, we saw a few different little subclasses. First one were binary acids, so just two-part acids here. For binary acids here, we're going to still reserve the term here hydro to remind me the hydrogen portion of it. We're going to have a blank depending on what the counterbalancing ion is, and then we're going to end it off with ic acid. So think hydrochloric acid, hydrobromic acid, those are just two-part acids. When do we get things that are more than binary here is when we actually throw in those polyatomics. If my polyatomic ends in ATE for the time being, we're going to drop the hydro altogether, and we're just going to have this ending portion as something ic acid, nitric acid, so ferric acid. Okay, those would change from the ending polyatomic ATE to IC acid. The other common ending here for polyatomic is ITE. For ITE here, it's going to be something OUS acid. You'll notice for these last two categories here, we know it's not binary because I've completely dropped the hydro. While knowing the thing is still an acid, I know it does have to always have an H with it anyways. Okay. One other family of ionic compounds here, we had the family of hydrates. So this part here was new to us this year. As that name suggests here, hydrates are things that are hydrated. They're going to contain water inside. I want to just emphasize here, as a hydrate, we're looking at a solid. We're looking at an ionic compound with its structure. It's still remaining as a powder, and yet it's somehow soaked in some water like a sponge soaks up water. In this case here, we're going to still have the regular name as we would practice later on. That part there will be the anhydrous part. Anhydrous just means dry. Okay, no hydrate just yet. And then what we're going to add, this is the one and only time for ionic compounds we actually use the prefixes here. We'll use that prefix like mono, di, tri, tetra, things like that. That prefix will actually indicate for me how many waters, although we ended off here, that prefix hydrate. So pentahydrate, hexahydrate, okay? The prefix will tell you exactly how many waters there are. This will be indicates water. Remember, all these ionic compounds here, because we are dealing with electron transfer and charges, all of these end up forming a lattice structure. They're never so simple as just one single positive, one single negative. We work out the ratio so that the charges in the lattice here can cancel out, but we do end up having a repeating portion. So let's say this is my Lego block. That Lego block, kind of like an empirical formula, that's going to be called your formula unit. That's the building block this lattice structure is based off of. And yet what ends up happening here is, because I sort of repeat these alternating charges, we end up forming a big lattice structure so that I don't really care exactly how many positives or negatives there are. We just care the ratio that's represented in the compound. You're going to find, as you look back through our notes here, majority of this chapter here was focusing in on ionic compounds. That's where we got all the variety from. We saw we needed to use prefixes, but just for this very last category, we actually use these prefixes a lot more for the other type of compound here. These guys here were your covalent compounds. Just for simplicity here, covalent compounds, we're looking at non-metal compounds. So non-metals are on the right-hand side of your table. In that case there, this is sort of more what we expect if I write, for example, a molecule like CO2. First thing you do is you check, is it non-metal? Is it non-metal? Well, both of them are on the right-hand side, so both of them are non-metals. This one here is going to be molecular. They actually are just a simple molecule, just a simple blob. They don't form this repeating pattern, this sort of alternating charges, things like that. This is quite simply one carbon that's bonded to two oxygens. So it's just a blob like that, okay? Maybe over here, there's another CO2 here. These are just individual groupings just hanging out by themselves. For this one here, we will utilize our prefixes. So use prefixes. And if I can just remind you here, let's just count to 10. Back on your grade 10 table, they were still very nice to you. They actually gave you these prefixes. At least up to 10 here, we do want to memorize some of these prefixes. So starting with 1 here, we're going to start off with mono. 2 is going to be di. 3 is tri. 4 as a tetra. 5 is penta. Think about your shapes here like pentagon, tetrahedral. 6 is like a hexagon, so hexa. 7 is hepta. 8 is going to be octa. 9 nona. And then 10 we are going to have deca. All right. So that's basically chapter 4. The tricky part in that part there is they might actually mix some of these compounds. You might run into an acid, might run into a hydrate, and then covalent. First thing you want to do is you want to recognize what type of compound it's representing. And based on that type of compound, use the appropriate nomenclature, the appropriate naming for that part there. Okay, so we'll do a couple of these just for practice. So remember, you need to be comfortable going from the symbols to the word name as well as the word name to the symbols. So let's start off here, ammonium oxide. Give you hydrobromic acid. Let's do manganese 4 nitrite. Cesium, I'll give you one that's a hydrate here. So cesium sulfate. Trihydrate. Let's try some the opposite way as well. So HClO2. We'll do SRF2. 7 water. We're going to do Se4Cl9 and FeMnO4 with a 3. Okay. So as always, I encourage you just to pause the video, try it out for yourself, and then you can just check your work with me afterwards. Assuming you've done that here, just using your polyatomic sheet here, I would encourage you just to memorize ammonium. Ammonium is your polyatomic grouping here, NH4. It is covalently bonded together, but it has an overall charge of +1. When I try to bond it with oxide, oxide comes from oxygen here. Oxide here would have a -2 charge. So when I work on my ionic compound, I know it's going to be a lattice, but at least the ratio inside the lattice has to cancel out positives and negatives. So in this case here, I should have 2 ammoniums for 1 oxide. So let's just put here NH4, because I have 2 of the entire grouping, I'll leave that in brackets. So NH4, there's 2 of them, but we're going to have an oxide on the far side. Okay. I know this ends up repeating and lattice and whatnot, but at least Lego block wise, for every 2 ammonium groupings for 1 oxide. Second one here, it is definitely an acid, but it still has this word here, hydro. That tells me here we're probably a binary acid. Binary is just a 2-part acid. Acids should have H, and then the bromic here should be obvious enough here. It's just going to be Br. When you have elements that have 1 letter, it has to be capital. If it's 2 letters, the first letter still has to be capital. Okay. This third one here, be careful, it is talking about manganese. It is not magnesium. Magnesium, Mg, is an alkaline earth metal. Manganese here in that transition metal section, it does happen to have that 4 of a charge, so Mn +4. Nitride looks like nitrogen, so it's 3 away from noble gases, so N with the -3 charge. And then we're just going to, again, mix and match those charges there. They both go into 12, so I would need Mn, 3 of them, to counterbalance nitrogen, 4 of them there. Okay. This fourth one here, we have cesium sulfate, trihydrate. Yes, every now and then the sulfate, they sometimes spell it with F or PH. More importantly for us here is this ATE ending. Because it's sulfate as opposed to sulfite, sulfate here is SO4 -2. So when I'm matching it up against cesium, cesium is an alkali metal. As an alkali metal, it's going to just have a +1 charge. That means then I need CS2 SO4. In this case, I only need 1 of the sulfate grouping. You don't need the brackets. I don't want to see those. I don't need you to identify for me that's a polyatomic. I would recognize that. And this one here being the hydrate, I'm the 3 hydrate. We're just going to put a dot to represent with. This is the cesium sulfate compound, but this has 3 waters associated with it. Okay. Going the opposite way now, we have HClO2. So this is not a binary acid, it's hydrogen with ClO2. ClO2 here is the chlorite grouping. So an acid that ends off with ITE, we're going to change the ending to OUS. So instead of just plain old calling it hydrogen chlorite, we'd rather change it to the acid name here of chlorous acid. Okay. And yes, we dropped the hydro altogether. I already know that this is an acid, so I know it's going to come along with hydrogen. We have our SRF2, so SR is going to be strontium. We have fluoride for the F. And then this one here, also a hydrate here. This is the only time in ionic compounds that we actually use prefixes. So utilizing the prefixes here, the prefix for 7 is hepta. So we're going to say hepta. I do sometimes get very funny endings here, heptawater. This is just the hydrate family. So we're just going to say heptahydrate with a 7 hydrate. So we are still a solid structure, but we've somehow been embedded by 7 waters, just like a sponge soaks up water. This next one here, a little bit tricky. You recognize Se as well as Cl. They are both nonmetals. Because they're both nonmetals, we're talking covalent compound, which means that this is molecular, which means that there's no charges or anything like that. We just use prefixes to identify exactly how much there are. So Se4, let's say tetraselenium. If the first prefix was mono, I can leave it out, but it's not. It's tetra. There's 4 of them. And then we have 9 chlorines. So we're going to put here nona chloride. There's 9 chlorines associated to this molecule, and the prefixes tell me exactly how many of each nonmetal there are. Last one for our practice here, we had FeMnO4. Fe as iron is one of those ones that are potentially multivalent. It could have multiple charges. Let's try to find out the charge here based on the ending here. This MnO4 grouping here is permanganate. That part there has a -1 charge. With the bracket, it tells me I have 3 of these permanganates. I just need 1 iron to counterbalance the -3 charge, so that means this has to be iron. We'll put the bracket to identify the charge there. Iron 3. This permanganate already has that common name, permanganate, so I don't need to change the ending. And like most polyatomics here, they very often end off with ATE or ITE. Okay. So see how you did on those practice ones there. Keep going through your worksheets and whatnot. And we'll finish our summary here doing a quick overview of Chapter 6, which was on chemical reactions. So here, Chapter 6. We learned about 6 very simple types of reactions where we can sort of look at some patterns, we can make some good predictions with what products are expected to form. So you will need to know the names of these reactions here. We'll start off with a synthesis reaction, which is S for shorthand. Just like when you synthesize something, you just sort of combine and put them together. A synthesis reaction here involves A and B, usually elements. They glue together, and then we end up forming AB as our compound. Very often we're looking at ionic compounds, but this could happen for covalent as well. We could do the opposite of a synthesis here, which is a decomposition. We can actually break it apart. Let's use D for that. Also really easy to recognize because this is the one reaction where we just have one compound and then suddenly an arrow. Well, the only thing that can happen is it can end up falling apart. In our Mohs chapter, we had seen dissociation where we end up forming ions. In this case here, decomposition ends up forming just their elemental states. So there's a decomposition falling apart. Third one here we're going to do is combustion. Combustion is a fancy word for burning. And the nice thing about a combustion is we can actually predict 3 out of the 4 chemicals. So we have whatever the chemical we're looking at. We have to have oxygen when we're burning something. Whenever oxygen is by itself, it has to be an O2. And then after the burning reaction, assuming that it's complete combustion, we're going to end up with CO2 and we're going to end up with water. Right? That's, I mentioned here, it has to be complete combustion. When the fire just starts, maybe there's not a lot of oxygen around, maybe the fire is taking a little while to get going, you could every now and then get incomplete combustion, where instead of fully getting the oxidized carbon dioxide, sometimes we'll end up with CO, carbon monoxide, or even carbon as soot, typically is a dirtier or a tarnished looking flame. But for us, we're just going to pretend full combustion here, fully CO2, fully water. Obviously, if you end up burning things that have more than just C and H and O inside, let's say I burn things with sulfur, I need to have maybe sulfur dioxide or nitrogen dioxide. So there are more fancy combustions as well. For those ones, they'll probably hint at what the products are and just get you to do the balancing part. But at least for the predicting part here, that's what we can leave it at. We then did 2 types of replacement reactions here. Dealing with a single replacement first. Single replacement here, let's just do SR. For a single replacement, as the name suggests, we have one person that's by itself, and we have one person that's coupled up. Depending on whether the person by themselves is metal or non-metal, it's always going to be a, let's say in this case here, metal fighting the metal for the compound. Or if it's a non-metal, A would fight with C. If the reaction happens, the metal replaces B, we're going to end up new compound A and C, and poor old B gets kicked off. Right? For this one here, we saw that the reactions, they don't always happen. We needed to check something called the activity series. The activity series here gave us who ends up forming the stronger bond, who's able to replace another. If I were higher up on the activity series, I can kick off anyone lower than, but it cannot happen the opposite way. Moving on from there, 5th reaction we'll look at is a double replacement. Sometimes also called a double displacement. So there's 2 things that are sort of swapping up. In this one here, regardless of who's more active or who's less active here, we always end up with the same products anyways. So for this one here, you don't need to check activity series. You're just going to switch partners here. Just make sure after you do the replacement, every compound should have one metal portion, one non-metal portion. So A is going to be bonded with D, AD, and then we're going to have C is the metal, so C comes first, and CB, we're going to get sort of that alternate combination there. Now, most of these ones here being ionic compounds, it's a little bit hard to mash a powder and a powder together. It's not impossible, but solids have really low energy. So usually what we do is we dissolve it in solution first. We break up some of the ions, we make the ions meet each other a little bit easier. So for this one, instead of checking the activity series, I want you to check something called the solubility chart. The solubility chart tells you who's going to be soluble, who dissolves, who doesn't dissolve here. If you remember our solubility chart, we start off checking compound by compound. We look at the negative part first. We then mix and match it with the positive bit that comes afterwards. And we try to figure out, for that combination, does it say the thing is soluble? Soluble meaning the thing dissolves. I'm going to put AQ for that. Or does it say something that is either low soluble, or the terminology here can be insoluble, not really dissolved at all, and we're actually going to use S for there. For this type of reaction, because they typically occur in solution, we can go through, for a properly worded question, the reactants should be aqueous, right? The whole reason of dissolving them was to help them mix and match easier. On the right-hand side here, there's not as much guarantee. They could both be solid, they could both be aqueous, to finish that part off. Last type of reaction here was actually a special case of double replacement. We'll call this one here a neutralization reaction. During a neutralization reaction, what's being neutralized is an acid actually cancels out a base. So an acid here, typically, I'm just going to write it as HA. The acid brings the H along. We're going to neutralize it with the base. The base here happens to have the OH, so I'm just going to say BOH, where that B here can be anything. Okay. Well, it is a double replacement. It's a compound and a compound. These ones here typically are going to already be in solutions for them to show off their acid and base nature. We're going to swap our partners here. I'm going to end up getting B with A. So that's going to be generically called a salt. A salt is just going to be some ionic compound. And then because the H is always going to bond with the OH, we're always going to form water as a product. So you could write it HOH, or you can just say H2O there. And then we'll do our balancing like we do normally. So for those ones there, remember the key words. We wanted to identify what type of reaction. We'll classify it. We're going to make a prediction. We're going to guess at what the products are, what the combinations, what the new elements, what the new chemicals on the right-hand side are going to be. And then we're going to balance it to make sure mass is conserved. So these 6 reactions above here could actually come along with some sort of heat transfer. This is where we get our endothermic and exothermic from. We'll just do our memory aid here. For an endothermic reaction, heat enters, heat comes in. So if I either do a demo, if you actually see this reaction here, you'll see this reaction absorbing in heat. To show that, we're going to actually put the heat term on the left-hand side. A plus heat ends up becoming B. If heat is exothermic, heat's going to leave. For heat leaving the system here, heat exiting here, we can actually have C becoming D, and then we're going to have, I can say plus heat, I can say more generically here plus energy. We've seen reactions that give off light, that's still classified as exothermic there, but you see that the energy term is on the right-hand side. Because we are always part of the surroundings here, if I have, let's say, a test tube, where the reaction is giving off energy, my hand is going to end up feeling all this energy on the outside. My hand is going to feel hot. Whereas on the other case here, if the reaction here is actually stealing away heat, it's actually pulling heat inside, it's stealing heat away from my hand. So what's going to happen is I'm going to end up surroundings, end up feeling cold, whereas in the other case here, I end up feeling hot. We could represent this one other way using energy level diagrams. So I'm just going to plot my axes here. We usually plot this axis here as enthalpy, the energy inside the system. You could totally put time on this axis. So as the reaction proceeds, or later on you're going to see we're swap it out for reaction as well. A is going to start off with some amount of energy. I don't exactly know what it is. A ends up stealing a bunch of heat, grabbing heat from the surroundings, pulling heat away from your hand. As it ends up chemically combining to become B, B has now locked away all the energy inside, so B is now at a higher energy reading than the A is. In regular Chem 11 here, usually what we would do is we just simply connect the dots. Okay. First thing that we're going to learn in Chem 12 is even though there is a slow, steady climb towards this B, there actually is a little bit of an energy hill that actually decides whether the reaction is fast or slow. To track this as a change here, we're going to identify here something called a delta H. Delta H here is a change in energy. Do we have more energy or less? In this case here, bigger number minus smaller number. Endothermic means delta H is positive. If I do exactly the same here on an exothermic reaction, just giving you some variety here, I might label this here either potential energy or just H for enthalpy. Right, it's the energy inside the system. We will use that reaction coordinate, a reaction axis, so that way I can read left to right or right to left. In this case here, C starts off with some energy. I don't know exactly what it is. D ends up falling downwards. D is lower energy because of all the energy that got released to the surroundings that sort of went into your hand. That's when we end up feeling hotter. Again, Chem 11, we usually just connect the dots. We just care about the start and finish. But in Chem 12, first thing we'll do is we'll put an energy barrier on both sides. As you try to track for me the delta H, the change in energy, in this case here, the change in energy, you notice delta H points downwards, so this change in energy is actually going to be negative. So two ways of telling endothermic, heat term on the left side, or the delta H being positive. Two ways of telling exothermic, the heat term on the right side, or the delta H here being negative. You have to be given information about whether the surroundings get cold or hot to predict whether it's endo or exo, but we could add that heat term in to just give us some more extra information on what we expect for the reaction. So we'll just end off with these last equations here. Here's our three words. We're going to make a prediction. We're going to make a guess at what the products are. We're going to balance. We're going to try to add in the coefficients, make sure all the elements are accounted for, and then we're going to classify it as one of those 6 types of reactions: synthesis, decomposition, double replacement, single replacement. You just want to figure out which one it is. Okay? So I'll leave you with these two here. Let's start off with Al reacting with CuCl2. Okay, just going to give you the arrow. Okay, see if you can make a prediction. What do you think gets formed? And then one more here. Let's go O2 and C2H6. Okay. This one looks a little bit scary here, but again, my hint here, we have oxygen here as a reactant, so probably what type of reaction is this? Make sure after you make a prediction, you still want to make sure you've written the correct compounds, and then we'll do their balancing here. Okay. Encourage you just to pause the video, try it out for yourself. And if you just want to check your work with me here, this first one here is a single replacement. We have aluminum and we have copper as a metal. They're both competing for chlorine. I should be checking the activity series for which one's higher up. Aluminum is actually more active, so aluminum forms a stronger bond. Aluminum has no trouble kicking off the chlorine. I will get a combination of aluminum with chlorine, and then poor old copper gets kicked off, but I still have to make sure that I've written the correct compounds, the correct symbols, the correct formulas for these ones here. That's why we did that practice earlier. Well, Al has a +3 charge, chlorine has a -1. This would need to be AlCl3. I always get asked here, well, what charge is copper here? Copper here is actually just plain old copper metal. If you did this reaction, you'd actually see solid particulate matter actually come out. It was charged over here, so it was +2, but it actually has gained some electrons to actually solidify out. Now I'll say, wait a second, the numbers don't balance. That's fine. Coefficients are the very last things that I add in anyways. In this case here, I see that chlorine is either 2 or 3. Both of them go into 6. So let's make this 3, let's make this 2. That screws up the copper, so let's make this a 3, 2 aluminums. There we go. And our classification here, I'll just say SR, single replacement. This other reaction here, I wanted to make a comparison. Hey, it's also an element and a compound and whatnot. One feature I mentioned here was, hey, oxygen is a reactant. It isn't just any plain old guy by himself coming in to replace. This is probably going to be a combustion style reaction. A combustion reaction here, 3 out of the 4 things are fixed. On reacting with oxygen, I end up forming CO2 and water. I pretend that we are a complete combustion here. We're going to try to do our balancing here. We're going to run into a problem pretty soon. I have 2 carbons there. Let's put that 2. 6 hydrogens. I need that 3. In this case here, I'm going to end up with the odd number of oxygens. That's not going to pair up nicely with our diatomic oxygen here. So our strategy, as we've seen before, let's take our whole equation and let's just double the entire equation. By doubling the entire equation, it ends up keeping everything still lowest terms, but it ends up avoiding any fractions. By doubling it, this becomes a 2, a 4, a 6. So in total, that's 4 times 2, 8 oxygens plus 6, so 14. I would then need a 7 to finish balancing it all. Okay? So keep on doing your review. Just let me know if you have any questions. Thanks, guys.